it going?
Yeah.
Alright, so we have the Steiner-Lehmus theorem, and what the Steiner-Lehmus theorem says is you have a triangle ABC, here, as shown, and you draw angle bisectors like so. Right there. And another one right there. And if it happens to be that these two are equal lengths, then we know that these two are equal. That is, ABC is an isosceles triangle. So we have legs AC and BC, isosceles. Right. Now, the converse of this theorem is really easy to prove. Let's see, which would be that if we have an isosceles triangle with AC equals to BC, then we'll have that the angle bisectors are equivalent. Like so. Is that good? Right, now to prove the converse of this, we draw two angle bisectors like before. Like so. Okay, and since these are bisectors, okay. But we know that this angle over here is equal to this angle over here, since this is an isosceles triangle. And we have that this angle is equal to this angle right here, right? So this angle, and this side corresponds to this angle, and this side. So we basically have that triangle A, B, we'll let this be E, let this be D. So we have ABE is congruent to triangle CBAD. Right? And because of that, we have this side of triangle ABE is equal to this side of triangle BAD. And that's how you prove the converse. And now what we showed here is something that we call an equality chasing proof. Equality chasing, right? That's because we showed, we assumed A equals B, C equals D, and we move on, and we see that, yes, indeed, X equals Y, right? In our case, that, this segment here and this segment here are equal, right? And most people would think that the converse of the converse itself, which would be the Steiner-Lehmus theorem, is the same way. We can have an easy proof where we assume a couple things, take the chain along the line and finally get that this triangle was indeed isosceles, that AC is equal to BC, right? But sadly, this is not the case. In 1840, a mathematician named Lehmus, right? He proposed this problem to another mathematician named Sturm, right? He wanted to prove it, but he wasn't able to. So Sturm, he sent it out to a bunch of other mathematicians, and Steiner, right here, Steiner, this guy, was one of the first to prove it, right? But of course, he didn't find a direct proof for it. Because if you first look at this problem, this looks entirely obvious. You have a bisector right here, another bisector right here. They're equal, And just look at it from, in an intuitive way, and you say, well, how could it not be true? But that statement in itself is pretty meaningful, That statement means that this is probably going to be easily proved by contradiction, but it's so basic at a level that you can't easily find a direct proof for it, ironically enough. And that's the point of controversy today, Is there an actual direct proof for this theorem. And now a couple mathematicians, claim to have proved that it's not possible. Conway has shown that you can't have an equality chasing proof, right? You can't have that, we assume that first that these two things are equal, right? X equals y, and then we have other things, and we finally prove that AC is equal to BC. And in his demonstration, he goes into the negative numbers, and he says if you have a negative length or even a complex length like line segment, and you had such a proof, it would also work for the negatives. And it turns out this statement is not true for complex and negatives, which that goes into much more needless detail, well, at least in our demonstration. So we won't go into that, but this just shows that this problem is not as simple as it looks. In fact, it's so simple that it's not, you can't have a direct proof, or so it seems, right? But we will show a direct proof, or a seemingly direct proof. But even a direct proof right here, that, we have a couple statements A, B, C, if A then B, if B then C, if C then such and so on. And then we eventually, arrive at the Steiner-Lehmus theorem, right? One of these chains right here, right, might be one of those things where you can't prove it directly. So, in a sense, we don't really have a chain of, simple implications where we have if, then, obviously. So it might not be direct. In a subtle sense, it might just be another proof by contradiction. And it's a problem that's actually being worked on, I mean, it's a pretty popular problem. But yeah, so it's not a simple problem as it looks. So here we'll show a direct seeming proof. Now the underlying theorems and lemmas that we use along the way might not be direct, but we'll ignore those for now and simply prove the theorem. Now what we're going to show is this thing called side-side angle congruence, right? And some of you may have learned that side-side angle is not a valid category for the congruency of triangles, and that's quite true. But what I'm going to demonstrate here is that there are a limited number of triangles that you can make with two sides and one angle that are fixed. And specifically, there are actually only two. So let's say we have an angle like so, right? And we fix a side here, right? So we are given a side of length C, right? And then we're given another side, right, of length, let's say of length A. But here, length A, okay, but here we aren't given the angle here. We don't know what the angle here is. So this angle could go on at any radius A around B, right? Now the circle intersects this line right here. This line we'll label L. This circle intersects line L at 2 points, here and here, right? So we only have two triangles that we can make, given a side, a fixed angle, and a fixed length A. Only two right here. And we can classify these two triangles here. And assuming that we start with an acute angle here, right? Assuming we start with an acute angle, then we see that the triangle that we make first would be an obtuse. The next triangle we make is an acute. All of these angles are acute. Right? That is, they are less than the right angle, which is 90 degrees. So we're going to use this towards the end of our proof of the Steiner-Lehmus theorem. And you will see how that is used later on. Okay, so now onto the proof of the theorem itself. We'll start out with the diagram. Okay. Right, we draw our triangle like so. Okay. Now we label it A, B, and C. Alright. And now draw the angle bisectors. Right? And label these intersection points D and E, like so. Right? And now we're going to need a helping line, so to speak. And this helping line will be right here. We want to make it so that we want to create a point F here, right? So that AF is equal to AE, but also DF is equal to BA, right? And we'll create these lines here, another one right here. Okay. So we drew these two helping lines for a reason. Okay. We'll see that these two angles, these two lines, segments, by assumption are equal. Right? We're trying to prove that the bisectors, if they're equal, then the triangle itself is isosceles. Right? But we notice something here, right? We see that this triangle with D, F, and A is congruent to B, A, E. Right? We have DFA is congruent to triangle BAE. Okay? Why is this so? Well, we have BA is equal to DF, right? That's a side. Okay? And we have, by assumption, EA is equal to FA. Right? It's another side. Okay? And our initial assumption, we have DA is equal to BE. Okay? So here, we have three sides. And by SSS criterion, we can say triangle DFA is congruent to triangle BAE. Alright, so what can we say about the angles? We showed that triangle DFA is equal to triangle BAE, right? Now we have to use this somehow to prove something about the angles, right? And we're going to do it like so. Okay, let's see, the angle opposite side DF is this angle right here, which is FAD. Angle FAD, right? Start with that. So this angle right here, erase that. Just make that a little smaller. And so this angle right here, okay, it turns out to be equal to this angle. Why? Because AB is equal to DF, right? So they're corresponding sides of congruent triangles. So that means their opposite angles must be equal, right? That is, we can turn this triangle around to match with this triangle, and these two angles will overlap, right? So this angle, what is this angle? It is AEB, right? We also have angle ADF is equal to half of angle B. Now, how did we get that? Well, we got it because this angle right here is is congruent to this angle. And as we know, this angle has been bisected from B by this line segment BE. And by bisection we mean divided by half. So that's why we have angle ADF is equal to half of B. Because this is opposite side AF, and this is opposite side AE, and AF is congruent to AE in our triangle there, right? So that means these two angles are equivalent. Okay, so we've labeled a couple more things here. We have the intersection, which we label point G, and we have this angle, angle 1, this angle, angle 2, angle 3, and angle 4, and they're all part of this triangle AGE, right? And triangle BDG. Okay. And we notice that these two vertical angles, which I've labeled V, they're equivalent, because they're right across from each other, and they're vertical angles. And as we know, vertical angles are equivalent, or measure the same. And so we also know that the angles of a triangle add up to 180 degrees, right? So we have that 1 plus 2 plus V is equal to 180, and 3 plus 4 plus V is also equal to 180. So we have this thing plus V is the same thing as this thing plus V, right? So we have 1 plus 2 plus V is equal to 3 plus 4 plus V, right? And it seems pretty obvious, subtracting V from both sides, that angle 1 and 2 must be equal to angle 3 and 4. So let's write this out. Okay, that's angle AEB plus angle half of A, the bisection of angle A, is equal to angle ADB plus, let's see, angle 4, which is basically just half B. Okay? Alright, so now let's take a look at our diagram here, right? Let's take a look at our diagram, right? We can make a couple of substitutions, right? Angle AEB, right here, angle AEB. So this angle we've drawn here, we already know it's equal to FAD, right? So let's write that. Okay. But we see here, this angle half B, right here. We see that it's equal to ADF, right here, ADF. You see that angle? Yeah. So let's write that there. And can carry on here. Carry on here. So we've just made a couple substitutions here and here, kept everything else the same. And we have another identity right here. Okay? Now from here we conclude that angle FAB must be equal to angle BDF. So we consolidate it to a smaller equation. Now what is angle FAB? Angle FAB is this angle right here. This entire big angle. Okay? And all we're doing here is rewriting this top part, which is FAD and half A. So we have half A here and angle FAD here. And you can easily see it's just the entire angle FAB. And same thing here. We have ADB right here, and we have ADF right here. You can easily see consolidated into one big angle BDF, angle BDF. Okay, and now we're off to prove that this angle right here, FAB, which is apparently equal to angle BDF right here, are indeed obtuse. Now the picture suggests it, but we haven't exactly proved it yet, and that's what we're going to do. Right? First of all, we show that angle ADB plus half B is equal to angle AGB. And this is so because consider triangle ADB right here. Okay? So we're going to extract triangle ADB, right? Okay. And then we'll add on this angle. Okay. This angle right here. And then we have angle 3 and angle 4, just like in the diagram. Now, by theorem we know that this angle right here is equal to the sum of this angle. Okay? So what I'm saying is angle AGB, angle AGB is equal to angle 3 plus angle 4. Alright? But what do we see here? Angle 3, when you write it out with letters, we see it's angle ADB, that's angle 3. Angle 4 is simply half B, right? And we have that the sum of those two angles is AGB. But we have the sum right here. That's basically angle 3 plus angle 4, right? So that is equal to that, okay? But we have something else also, right? Angle AGB. Now let's extract another triangle here, okay? Draw it out. Now we're taking out angle AGB, so triangle AGB, okay? Okay. And this is our angle AGB as before, and we have half A, and we have half B. Okay. Now what do we see here? We have the identity that the sum of the triangle, the sum of the three angles of a triangle add up to 180 degrees. So we have half of angle A plus half of angle B plus angle AGB is equal to 180 degrees. Now we simply subtract these two angles from both sides, and we get a formula for angle AGB, 180 degrees minus, okay, minus, make some room here, minus half of angle A minus half of angle B. Okay. Now let's pull out the half, a bit of algebra. Okay. Right. Now, what we notice here is like that half of a big angle right here, angle A plus angle B. Now we know angle A plus angle B can't be more than 180, right? And it can't be 180 because we have three angles A, B, and C, right? So this has to be less than 180 degrees, right? So if angle A and B, so let's say some x is less than 180 degrees, right? That means that that angle divided by 2 must be less than 90 degrees. Right? So that shows us that this thing right here is acute. That adds up to an acute angle. Right? Which means that this entire thing right here must be an obtuse angle, right? Since if you have a straight angle right here, and if you have an acute angle right here, the remaining must be an obtuse angle. So therefore, angle AGB which is represented in this expression right here, must be obtuse. Alright? And since we settled that AGB is indeed equal to this thing right here, which is equal to this thing right here, and which is equal to this thing right here, we have AGB is equal to BDF is equal to FAB. So FAB, BDF, and AGB are all obtuse. And so we prove what we wanted. Okay. Alright, so we have two facts, right? We have angle FAB, this angle right here, is equal to angle BDF, this angle right here. And we have that they are indeed obtuse, right? But this is all we're going to need to finish our proof. And I'll show you how. Okay, we extract figure from the left, simplify things a bit, and we draw this diagonal right here, FB. Right? And we have the following assumed equivalencies. This segment here is equal to this segment there. Right? And this segment is obviously equal to itself. And we have this obtuse angle here. Now, we also have that, but what do we have here? We have a side, another angle, right? Side, side, angle, side, side, angle. Now, that by itself doesn't give us much. As we know, this criterion is notorious for basically not giving you a congruence of triangles. You know, unlike side, angle, angle, and side, side, side. But it gives us something, right? And we can see that. Right? So we have an indefinite line right here, and we know we have a fixed obtuse angle like so. And we draw a fixed length of length x, which terminates at a certain point, right? And then we have another fixed length, you know, with some angle, right? But we know that this has to be acute, right? This has to be acute, right? This angle is some acute angle, right? And it's some fixed length y, okay? So since we know it has to be acute, it has to be on this side somehow. Okay, so we have these bounds here, okay? So this fixed length here is free to pivot around as long as it's between these two boundaries right here, right? And then in a circle, right? But as we see here, we have a fixed length, and if it were to deviate by another angle, like so, we would have a different length, y prime, not equal to y, right? So it's a bit of a method of contradiction in a sense. It's not really direct, okay? And this is where the direct proof pitfall comes in, you know? We don't really have an easy direct sense. We don't have like an angle side angle, therefore these two triangles are equivalent kind of way. You know, we rely on this kind of iffy fact, right? It's not really iffy in the logical sense, it's perfectly sound, you see? But we haven't proved it directly. All we know is that it has to be that it's a unique triangle. That indeed, this length y, this length x, and this angle, some theta, must give this one triangle, this unique triangle, right? This line segment cannot deviate any further from that, okay? So we have a unique triangle, right? FAB. So that means any triangle with angle theta, angle x, and angle y, angle theta, length x, and length y must be a unique angle. That is, if we have another triangle with the same properties, then it must be equal to this triangle, right? And we have that right here, right? With triangle FA and B. Okay? We have this angle, some length x, some length y. We have this triangle with some angle theta, length x, length y. And that means this triangle must be equal to that triangle. Since we proved by contradiction that indeed this is going to have to be, a different, the same exact triangle, because it's unique. That's what uniqueness is. There's only one triangle that has an obtuse angle, some length, and another length, right? And so it's a little convoluted, but what we've proved is pretty simple, right? We have triangle FAB is congruent to triangle DFB. Okay? Oh, sorry. That'll have to be triangle BDF. So we have FAB and BDF. Okay? Alright, so what can we get from here? Well, first of all, now we know that these two edge lengths are equivalent. Right? That is AF is equal to DB. Right? Okay? But what do we have here? Right? We have that AF is equal to AE by assumption. That's how we drew this point in the first place. So this is actually equal to AE. Right? So we mark that on our original diagram here. AF is equal to AE. Okay? Alright. So we proved that triangle FAB is congruent to triangle BDF. Right? Now what does that give us? We have two corresponding sides, AF, BD, or DB here, and by assumption we know AF is equal to AE. Okay? So that gives us AF is equal to DB is equal to AE. Right? And here I've pulled out the figure. This butterfly figure right here, consisting of A, E, G, B, and D. Okay, now notice triangle AEG. Okay, by assumption we have AD is equal to BE. Okay, those are our bisectors, and we assumed to prove the implication that those two are equal. Okay, so we have a side AD is equal to BD. Okay, now we have another side we just showed. Okay, AE is equal to DB. Okay, that's our second side. Alright, now let's draw a line segment connecting E to D. And easily we see that ED is equal to DE. So we have three sides that are equal to each other. Okay, so that gives us AED is equal to BDE. So triangle AED is equal to triangle BDE. Okay? So what does that tell us? Well, it's simple. We have triangle AED consisting of half angle A, triangle BDE consisting of half angle B. And since these are two congruent triangles, and these two angles are corresponding. That is, these two opposite angles, these two opposite sides, ED and DE, they're equivalent. So what does that tell us about the angles? They must also be equivalent. So half A is equal to half B. Okay. Alright, well, there it is. What we do here, we simply multiply both sides by 2. We get angle A is equal to angle B. and it's simple from here. We have by the converse of the pons asinorum, and we get AC is equal to BC.